Okay, so you plot out your two-dimensional stress element with the values for sigma x, tau xy, and sigma y and tau yx. And to create Mohr circle, what I would do is write down 2 points, the location of 2 points here. So our x point is going to be, the coordinates are going to be sigma x and tau xy. Okay, and the location or the coordinates of our y point here are sigma y and tau yx. Okay, so from the given information in the question, sigma x is 75 and tau xy is 125. Now there's a couple of different ways of doing Mohr circle. The approach I take is I'm not going to worry about whether these shear stresses are positive or negative. What I want to know is whether they're clockwise or anti-clockwise. So I'll just make a note of that. Tau xy here is anti-clockwise. Okay, so this arrow and this arrow here would tend to rotate the element anti-clockwise. So I'm going to write that down. It's 125 anti-clockwise. Okay? So that's going to be the coordinates of one of the 2 points for generating Mohr circle, 75 and 125 anti-clockwise. This y point then, capital Y here, the coordinates of that point, sigma y is 0 and tau yx is 125 clockwise. 0, 125 clockwise. Okay, so that's the location of my 2 points. I don't think I have a ruler, but what we'll do is set up 2 axes. So Mohr circle is plotted on your horizontal axis is your normal stresses, sigma minus sigma. And your vertical axis is shear stress. Okay, and again, different people do this slightly different. The way I do this is the vertical axis here is clockwise shear, tau clockwise, and down this way is anti-clockwise shear, tau ACW. Okay, so your axes, horizontal axis is normal stress, vertical axis is shear stress, with positive here being clockwise and negative is anti-clockwise. Can you make that out? Okay? This is positive normal stress, negative normal stress, clockwise shear, anti-clockwise shear. And just plot out those 2 points then. So our 2 points were, our x point is 75 and 125 anti-clockwise. So okay, so this is, if I come across 75, so 1, 2, 3, 4, 5, 6, 7 and a half this way, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a half down this way, I'll have a point here. So this point is my x. That's my original x side of this stress element here, was 75 and 125 anti-clockwise shear. Okay, so that gives me this point down here, 75 and 125 anti-clockwise. Okay, and that point there represents, as I said, everything that's happening on the x side. Everything that's happening on the x side of that stress element there. 75 and 125 clockwise. anti-clockwise. Okay? My second point then, the Y point here, is going to be 0 and 125 clockwise. So 0 normal stress, 125 clockwise. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I just have the arrow in the wrong place there, but that is my Z point. Y point here. So Y is just here on that axis. And that location of that is 0, 125 clockwise. Okay? So to construct Mohr's circle, what I need to do is just to connect those 2 points, and that will become the diameter of my circle. Okay? Now the 2 of those are going to cross at the center of the circle here, or rather that diameter is going to cross the axis here. So the location at the center of that circle is going to be halfway between 75 and 0. So the location at the center of that circle is 37.5 normal stress. So that point there, 37.5 0. Okay, so that's the center of the circle. Put a compass down in that, scribe out a circle, and then you'll be able to read off anything you like from that circle afterwards. Okay. This compass slipped a little bit there, I think. Okay. So that's Mohr's circle constructed. As I say, really what you need to do is plot those 2 points representing what's happening on the X side of the element here, and the second point representing what's happening on the Y side here. So 0 and 125 clockwise. From that then you should be able to read off your maximum normal stress will be this location over here on the very right hand side of the circle. And I can estimate that here, so that is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 20, 30, 40, 50, 60, about 170 megapascals of normal stress would be the maximum normal stress on that part. Okay? The minimum normal stress will be over here on the left hand side of the circle. So that is 10, 20, 30, 40, 50, 60, 70, 80, 90, about maybe minus 95 megapascals over here. Okay? So about plus 170 and about minus 95 megapascals of stress are the maximum and minimum. Yeah.
In an exam, will we have to draw this out and use the values from the graph, or will we have to actually use the formula to get the pressure matches?
So typically you would have to draw it out on graph paper. You can use the values from the graph paper, or you can use the formulas for your answer.
So graph, so yeah, so you put down the graph answers and they're within a certain amount of reason, then you get the max.
Yeah. As long as the circle is constructed properly and you've read your values from the graph properly, you've read the correct values from the graph, then yeah.
98
roughly. Now we can work out the exact numbers on those, and I'll show you a version of the formulas that we looked at that corresponds to the values from your graph. So essentially what you're doing is you have a formula that gives you a way to calculate the radius of that circle. And if you say the centre plus the radius will give you that value on the right, the centre minus the radius will give you that value on the left, and it will give you a more precise value for it. Even if you're using the mathematical solution, I would always recommend that you do a graph anyway, because it'll for calculating the angles and the direction of those angles, I think the graphical method is hard to beat, visualizing the direction of those. So yeah, so those are the maximum and minimum values. So this one here on the right, that maximum value, that's sigma 1, your first principal stress, is that maximum value. Okay? And sigma 2 is your minimum normal stress, or the second principal stress, and that's the minus 95 on the left. The shear stresses then, the maximum shear stress, there's two values for it really. There's a maximum maximum shear stress in the clockwise direction is up at the very top of the circle here, tau max. So that's the maximum clockwise shear. And then you have the very bottom of the circle here, so directly underneath the center of the circle, this is tau max in the anti-clockwise. Okay, so the very top and bottom of the circle. And they should be both the same magnitude. One of them's clockwise, one of them's anti-clockwise. The same as here, your tau xy, one of them is anti-clockwise and one of them is clockwise, but they're equal and opposite to each other. Yeah? So the value for those then are going to be, say, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. A little bit more than 130, so maybe 132 or something like that. Say 132. And this one will be the same. Okay? Okay, so those are the values. Your maximum principal stress is about 170 roughly. Minimum principal stress is about minus 95, so it's a compressive stress. Your maximum shear stress is about 132. So one of them, your tau, let me see which is which. Your new tau xy will be this one here. So it'll be 132 anti-clockwise, and your new tau yx will be about 132 clockwise. But they're equal and opposite to each other. All right. Yeah, the angles then. So the angles on Mohr circle, we can work out. So the angle from our original x. So remember this point here. This is the original x coordinate, or the original x-axis maybe might be a better way of putting it, the original x-axis. Okay, so in our original stress element that we were looking at here, this was our original x, our original y. The original x-axis corresponds to this point down here where you have your sigma x and your tau xy. From the original x-axis to our new x-axis is going to be this angle here. Okay? So from the x-axis to sigma 1 is this angle here, and it's measured from the original x-axis to your principal stress.
What's that? What's that value you get?
That is 2 theta. Okay, so when we work out the actual angle of the principal stress in your part, measure that angle, divide it by 2, and that gives you theta, the angle of the plane, the angle of the inclined plane in your part at which the normal stress is a maximum. Okay? So you can stick down your protractor, measure that. So that is about 73, 74 degrees, something like that. So I'll just write down 74 here. So 2 theta is 74 degrees. So in the real world then, half of 74 would be 37. So I'll just maybe write it down here. 2 theta is equal to 74. So theta is about 37 degrees. Okay, so what that means is that our part in our original coordinate system had 75 megapascals of normal stress on it. If you were to look at that same part under the same loading conditions, but rotate your coordinate system 37 degrees anti-clockwise, so from our original x to our principal stress is 74 on Mohr circle anti-clockwise. If you were to, in the real world, look at your part, but look at it 37 degrees anti-clockwise from your original xy coordinate system, it would actually have 170 megapascals of normal stress on it. Okay? Same goes for the y-axis. So in our original coordinate system, there was 0 normal stress on the y-axis, in the y direction. This angle here on Mohr circle, so from your original y value to your minimum principal stress, sigma 2, that's also 74 degrees. Okay? So in the real world, in the original y direction, there was 0 normal stress. If you rotate 37 degrees anti-clockwise from your original y-axis, you would have minus 95 megapascals. So 95 megapascals of compression, 37 degrees anti-clockwise from your original y-axis. Okay? Now, so I'll just, on a separate page, I'll just draw that out. So in our original xy coordinate system, we had 75 this way, so 75 of tension, and 0 in the y direction. Okay, so that is x and y. Okay, so that's your original coordinate system. If we were to go 37 degrees anti-clockwise, so our new coordinate system would be something like this. Say x1, y1, or x prime, y prime, you'll see it as sometimes. So I'll just call it x1, y1, where that angle there is 37 degrees. So x1, y1 is 37 degrees anti-clockwise from xy. Okay? If you were to draw a stress element around that, so remember, this is on the same part, the shaft under torsion and an axial load. In this orientation, so the same part with the same forces on it, same torsion, same axial load, in this orientation, you would have 170 megapascals of tension this way, and you'd have 95 compression, or I'll call it minus 95 here. Okay? So it's the same part, under the same load, but just rotating your point of view, rotating your coordinate system a little bit, there is an actual plane or an orientation, a way of looking at that part where it actually has 170 megapascals of tension on it. and 95 megapascals of compression on it. Okay, and that angle is 37 degrees anti-clockwise from your XY coordinate system. Okay, so your new x-axis is 37 degrees anti-clockwise from your old x-axis. Your new y coordinate, your new y-axis is 37 degrees anti-clockwise from your old y-axis. And that corresponds to the 74 degrees from your x to your principal stress on Mohr's circle. So that 74 degrees on Mohr's circle, that corresponds to 37 degrees in the real world. Okay? All right. Yeah, so that plane there, or that orientation, those are your two principal stresses, and that's the angle at which they occur. All right, so that's the principal stresses. The other thing we can get from Mohr's circle then is the maximum shear stresses. And as I said, they occur at the top and bottom. Oh, actually, sorry. Yeah, what about the shear stresses in this case here? So remember, we've gone from our x-coordinate, we've gone 74 degrees. We've gone 74 degrees anti-clockwise, and we're talking about this point here where the normal stress is 170. What's the shear stress at that point? So remember, shear stress is your vertical axis. What's the shear stress at that point? Oh, sorry. So just at the very right-hand side of the circle, what's the shear stress here at this point? Zero. And likewise, what's the shear stress over here? Zero. So I haven't drawn them in here, but your shear stress here would be 0, 0, 0, and 0. Okay, so your shear stress is in that orientation. There is no shear stress. The part isn't under any shear in that orientation. Okay? And that's a feature of principal stresses. The principal stresses, the normal stresses will be a maximum and minimum, but there are no shear stresses. Do you have a question?
Is that to do with the fact that the circle's center point is on the vertical x-axis?
Yeah, yeah. Well, graphically, yes, that's, yeah. It's to do with the stress transformation equations, really, I suppose. The circle is just a representation, a graphical representation of those equations. Okay. What it is, if you look at those equations, there's some value of theta at which the equations for normal stress are maximum, and at that same angle of theta, the equation for stress transformation equals 0. Okay. All right. So that's the normal stresses, or the maximum normal stress and the minimum normal stress, which is your principal stresses. The other thing you can get from Mohr's circle is the maximum shear stress and the angle at which that occurs. So that is the top and bottom of the circle here. Okay? So this point up here and this point down here. Now they're equal and opposite. They're about 132 megapascals of shear stress. One of them is clockwise, one of them is anti-clockwise. Yeah, we'll see in a minute, but they are equal and opposite to each other. They occur on Mohr's circle, say, relative to our original x-coordinate. What's this angle here going to be? And I'll call it phi here, so I'll call it 2 phi rather on Mohr's circle, but in the real world that'll be phi. 2 phi. Okay, so what's that angle going to be? 16, yeah. So if we know that this one is 64, this one will be 16 degrees. So, and another way of looking at that, is that the angle on Mohr's circle, the angle between your principal stress and your maximum shear stress down here, on Mohr's circle that's 90 degrees. So we could say that as 2 theta plus 2 phi is equal to 90 degrees. Or in other words, on Mohr circle, the maximum shear stress is located 90 degrees from the principal stress. Now translate that back into the real world. We need to get half of these angles. So in the real world, the maximum shear stress is located 45 degrees from the maximum principal stress. Okay? And if you remember the cylinder of brass in the hydraulic press example, the maximum principal stress in that case was axial, but when the part broke, it broke 45 degrees from the axis. So the maximum principal stress was straight up and down in the axis of that cylinder of brass, but the maximum shear stress was 45 degrees from the principal stress. If you were to graph that out on Mohr circle, they'd be 90 degrees apart on the circle. Okay, so anyway, we can figure out from the circle, if we know that this is 74 degrees on the circle, 74 from 90 means this must be 16 degrees on the circle, and it's 16 degrees clockwise from X to the maximum shear stress. So back in the real world, phi would be 8 degrees. So we could plot out a new coordinate system. Let's say if that's our original XY there, our new coordinate system would be 8 degrees clockwise from the original XY. I'll call that X2, Y2, or X prime prime, Y prime prime. So it's a little bit exaggerated here, that's a bit more than 8 degrees, but let's just say, to make it more visible here, in this orientation, so 8 degrees clockwise, 8 degrees clockwise from our original X, we have a new X, 8 degrees clockwise from our original Y, we have this new Y axis. In this orientation, so 8 degrees clockwise from our original X, we have 132 megapascals of anti-clockwise shear. So here on our new X side, we have an anti-clockwise shear of 132. And 8 degrees clockwise from our original Y, so that's 16 there. 8 degrees clockwise from our original Y, we have 132 of clockwise shear. So up on the Y side, we have clockwise shear of 132. Okay, so in this new orientation, 8 degrees clockwise from our original axis, we have 132 and 132 anti-clockwise and clockwise there. What about the normal stresses in this orientation? So if we go back and look at Mohr circle again, say here on our maximum shear stress at the top of the circle, so that's our new tau yx, or tau y2x2. What's the normal stress at this point? Not quite zero, so this is zero over here. So 37.5. So the coordinates at this point here would be 37.5, 132. And the coordinates of this point down here would be 37.5 and 132 anti-clockwise. So what that means is, going back to this stress element here that's 8 degrees rotated clockwise, we're actually going to have 37.5 this way, 37.5 this way, and 37.5 this way. Okay, so in this orientation, 8 degrees clockwise from our original coordinate system, you've got loads and loads of shear stress, the maximum shear stress on the part. There is a normal stress, but it's balanced in all directions. It's like a hydrostatic stress, like a pressure that's the same in all directions. Okay, so the part is in tension equally in this new X direction and the new Y direction. Okay. And that's probably as much information as we can get straight away from the graph, but I think you'll agree that's a fair bit of information that you can get from just plotting down 2 points, connecting them with a line and scribing a circle with a compass. You can get a fair amount of information from Mohr circle. The next day what we look at is, there is a version of the stress transformation formulas that effectively allows you to work out the center and radius of so this version of the formula here, sigma theta is equal to sigma x plus sigma y over 2 plus or minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. It looks complicated enough, but sigma x plus sigma y over 2, that's the location of the center of your circle. And the square root of this squared plus this squared, that's the radius of your circle. So we look at that next week. So you can plug in the numbers into that and it'll back up what we have there on the... Thank you.